Hello everyone, my name is Theo and this is my update for June 22nd. So I'm on a Stoic project which is adding sparsity support to Triton. So in case you haven't seen them before, I saw these slides from Aria, but I did, essentially what we want to do is we have a sparse matrix and we want to assign them some sparsities. So for example, we'll break them into tiles. In this case, we'll have 4. And for each of these tiles, we're going to assign them either dense or sparse. And after that, we're going to kind of accumulate them into an array of all of the sparse tiles and an array of all the dense tiles. And we're going to pass this to our algorithm. So this can be the dot product, or it can be a scalar, adding a sparse matrix to some scalar as well. So the part I'll focus on right now will be dot products with another matrix. So when we have these sparse and dense tiles, this is what the algorithm kind of looks like. We have an accumulator, and for each of these tiles in a sparse row, we're going to compute the dot products and accumulate them into our accumulator, and we'll do the same thing for the dense tiles. And in the end, we're going to store the results into the output tile. So here are some of our learnings so far. I'm able to set up my environment on Compute Canada, as well as running some just jobs. And I've learned a bit about Triton. I'm writing a few sparse kernels, which I'll talk about a bit later. And I also have a high level understanding of what is happening behind the scenes. So which passes are running and how does, the Python, so how does the Python side is binded with the C++ side of things. I've also learned a bit about sparse compilers. So I have some familiarity with the Triton IR, as well as different encodings that we have, which I think the one that we want to focus on is NV24. I've learned about GPU memory hierarchy and pipelining, as well as more recently, I've learned about how the workload is distributed on the tile, the warp, and the MMA level. So the first thing I'll talk about is the Triton Auto Tuner. And what the Auto Tuner is it's something that will compile and benchmark various configurations that we have. So example configurations could be tile sizes, or the number of tiles that we have in a group, or the number of warps. So you can think of them as basically hyperparameters that we can tune to improve our performance. And how the workflow goes is we have the kernel entry, which should pass in some input matrix and some configurations. The auto tuner is going to go through every single one of these configurations and benchmark the throughput. So throughput is the metric that we're interested in here. Once it finds the best configuration, it's going to run the actual kernel and more rigorously benchmark how that performs. What it kind of looks like is we have a graph here, right? So on the y-axis we have the throughput, and on the x-axis we have the sparsity level. So you can think of this as on the left side we have a completely dense tile, completely dense matrix, and on the right side we have a completely sparse matrix. And then we want to see, as we kind of vary the sparsity level, whether auto tuning is going to give us better configuration that will lead to better performance. So just to visualize this, let's say we have the input matrix A. We can have different tile sizes. So this example here is if we have a 2x2 element, that would lead to a 4x4 tile matrix. Or we can have a even larger tile, right? So a 4x4 tile is going to lead to this 2x2 tile matrix. So in reality, we have matrices that are a lot larger than the example here. So which means there are way more configurations that we can try out. And this is also kind of the motivation that we want to have something automated that can help us find what is the best tile size. So here is the kind of the big problem that we have. So right now, the user is using a predefined configuration, and they're forced to do this, and they have to pass in basically the decomposed sparse and dense tiles themselves. So as you can see here with the input matrix A, the user is responsible for picking the configuration, assigning the sparsities, and generating the sparse and dense tiles. And this is not very flexible, right? So we need to kind of shift this responsibility to our auto tuner so that it can take care of assigning sparsities and generating sparse tiles. So here is what we want to achieve. As you can see here, we have a sparse matrix, that's the input. And really the difference is we want our auto tuner to be able to try out different tile sizes and different configurations. So we want it to be trying out all of these different things and benchmarking them in order to figure out what is the best tile size. And once it has that, it's going to pass the generated sparse and dense tiles into the kernel. So we remove the responsibilities from the user, and we have this automated pre-hook that's going to do this for us. So here's the plan and challenges. And the biggest challenge that we have is Triton's pre-hook actually does not support generating new values, which is exactly what we want to use it for. This means we need to have some modifications. So the three big ones is, so the first, we need to be able to capture all these generated tensors for each configuration. We want to keep the best one for benchmarking. And when this is done, we want to be able to deallocate basically all the generated stuff that from the pre-hook. So we don't have any memory leak when we go on benchmark other matrix sizes in the future. The challenge has been figuring out how AutoTuner works and how the benchmarking framework works. So there's a lot of concurrency, which makes deallocation pretty difficult. This means if we do not deallocate these matrix or these generated tensors on the GPU, our GPU would run out of memory pretty quickly. So here is the progress I've made so far. I'm pretty close to having something fully functional. So far what I have is I'm able to tune a variety of different sizes. Some are medium, some are like even a bit larger sizes. But for those really large sizes, I'm running out of memory. This is because I'm not deallocating any memory. And the reason I'm not deallocating any memory is because when I do that, sometimes I get illegal memory accesses, and it's been pretty difficult to debug. And I'm pretty sure this means I'm deallocating something that's still being used. But when something is running concurrently, it's a little bit difficult to debug that. So that'll be my next step, which is to see what we need to do to make sure the memory is deallocated in a way that's safe. So the next thing I want to talk about is a bug that I'm working on. So the bug is for a mixed sparsity matrix like this, if there's one row that is completely dense, so all the tiles in here are dense tiles, the kernel is going to basically crash. So we did some investigation and we found out that the issue comes from the first loop, which is to compute the sparse tiles. So if this sparse tile row loop does not run, the program crashes. So we want to find out why. So from some initial investigation, we think the problem has to be with the software pipeline pass. And what this pass does is it brings data to local memory from the global memory. So down here are two examples. So on the left is node pipelining, and this is working fine. And what it looks like is when we are computing the sparse row tiles, for each tile, we're going to be loading from global memory and computing them. But this is kind of slow because loading from global memory is way slower than loading from local memory. So when we have pipelining on, so here are two stages, which corresponds to basically two loads before the loop actually runs. So as you can see here, before the sparse row actually runs, we're loading two tiles ahead of time into our local memory so that when we're actually computing, we would just be loading from the local memory instead of from global memory, which is an optimization that we're doing. However, this can be the cause of our problem because if there's no safeguard, right, if we're not checking that, okay, is there actually a sparse tile to be loaded? Like, is this loop actually executing? If we're not checking for that and we're just blindly loading chunks of data from the global memory into local memory, I think we can get illegal memory access issues or even just unpredictable behavior. So the first thing I wanted to do is pretty much add a safeguard and don't do these pipeline loads if there is no sparse tiles. So it's very simple, just a check to see if there's sparse tiles. If there are, then we will load them. If there aren't, then we don't want to do anything. This actually led to another bug, which is adding the if statement inside the kernel. So when I added the if statements, the kernel just crashed. And this is actually a bug from one of the Triton's internal passes. And basically the pass didn't implement, or the implementation, it didn't clean up all of the uses of the original if op when I was doing a rewrite on the kernel. And the solution was pretty straightforward, which is after we rewrite the if op, we are going to replace all the uses of the original if op. And this is actually fixed in upstream, but not in our branch. So once we have this changes in, it allowed the if op to work. And with the if op and adding into the kernel, it fixed the issue, and the fully dense row no longer crashes the kernel. But this is a temporary fix. So in the future, I will have to diagnose the core issue of why the software pipeliner is crashing the kernel. When there's, we want to see if there's a safeguard in place that is supposed to prevent this. If not, then we want to add that. And similar to the if op, this could be something that's already fixed in upstream, but I went through the commits and I didn't see anything directly related to this. So I'll have to kind of verify this in the future once we merge with upstream. And I think that's pretty much done when I'm recording this. And the next thing I want to talk about, and the last thing I want to talk about is work concurrency. So if you can remember, if you recall, this is our algorithm, which is kind of sequential. So for each of these tiles in a sparse row, we're going to compute dot products, right, and accumulate them for the sparse row first, and then for the dense row. What if we can parallelize this? So our question is parallelizing the sparse and dense loop improve the throughputs? So the potential trade-off is we can have more warp occupancy and more utilization, but that also means more synchronization overhead. Because now when the sparse loop computes and accumulates by itself, and dense loop does the same thing, in the end, they have to automatically add to the output tile, which means synchronization overhead. And so this is kind of what a pseudocode would look like if we make this change to make them running at the same time. Instead of a 1D launch grid, we're going to have a 2D launch grid. So the first dimension is going to decide which output tile the program is going to work on. And then the second dimension is going to decide whether the program is going to work on the sparse or the dense tiles. As you can see here, we have our output tile. And if the second dimension is 0, then we're going to work on the sparse part. And then once the accumulation is complete, we're going to add this accumulator into the output tile. And then we'll do the same thing for the dense. But notice here that we're doing this atomically, which means there could be contention, which could be overhead. So here are some initial results for a fixed matrix size. We can see the concurrent one is not performing as well as the sequential one. This is close, but we can say across basically all the sparsities. So on the x-axis here, we're increasing the number of sparse tiles. So as we go from left to right, we're going from dense to sparse. But we can see across the board, the concurrent one is not performing as well as the sequential implementation. So the next step would be to profile the concurrent loop and see if there's better ways we can launch the kernel. So the way I've done it is pretty naive. Basically, if it's 0, you work on a sparse. If there's 1, you work on a dense. But maybe there's better ways we can launch the kernels to improve the throughput. And the second thing you want to verify is also how much synchronization overhead is contributing to the slowdown. So we know synchronization has overhead, but we want to know how much that is, and if there's any way we can reduce this overhead. And that can also help us speed up the concurrent loop. So this is the end of my presentation. Thank you so much for listening. And if you have any questions or comments, please message me on Slack. And I really hope all of you have a very good rest of your day. Thank you so much.